Okay, so what does it say? That let's take any two integers a and b. B should be positive. Then there exist unique integers q and r such that a is bq plus r, where most importantly r lies between 0 and strictly less than b. Okay, so it's the usual division that we do. We divide one integer by the other, and we look for a remainder which is less than the divisor. If the divisor is positive, this is what we expect. Okay, and you are all familiar with all this, that this integer q is called the quotient and the integer r is called the remainder. It's a very fundamental property of integers, and later on we'll see when we do the group theory and ring theory that if any ring has this property, then we can say a lot about that ring, and in that sense that ring will be very close to integers. Okay, but yeah, those things will come later. So this is a very important property. It's the starting point for many other interesting properties of integers. Okay, and how do we prove it? We can prove it as a consequence of the well ordering principle. Okay, we all know what is well ordering principle. We discussed this yesterday, not yesterday, in the last class, that if we have a non-empty set of positive integers, it has a least element. That's well ordering principle, and we are going to apply this to a suitable set. And before that, of course, this notation comes up time and again, so we might as well fix it here. That is absolute value of a is a if a is positive and minus a if a is negative. This is something that we all know. Okay, so let's see how we prove this division algorithm as a consequence of well ordering principle. Okay, so we have to consider a suitable set. So we'll actually pick this remainder as the least positive element or least element in some suitable set. Okay, so if we want to see it as the least element of some set, then like we will take a minus bq type of integers. So a minus bn, we'll take this set. Okay, we'll take this set a minus nb, where n runs over all integers, and a minus nb should be non-negative, because recall well ordering principle, it applies to any non-empty set of non-negative integers. Need not be positive, I can input 0 also. And this is because we allow the remainder to be 0. That's why we have kept it like this. The remainder should come as the least element of this set. Okay, but that least element should exist. For that, this set just has to be non-empty. So we have to show that this set is non-empty. Okay, so how do I show that this is non-empty? Well, we just have to produce some element here. Okay, I just have to find some n for which this is non-negative. Okay, that's all I need. And one thing we know that b is positive, so b is at least 1. Hence, if we multiply mod a and b, it is certainly bigger than equal to mod a, because b is at least 1. And we know that mod a is always bigger than equal to minus a. So in other words, if I take it to this side, so a plus mod a times b is non-negative. So I can pick my n to be minus of mod a. Okay, so if I put this n to be minus of mod a, so I'll have a plus mod a times b, which has to be positive or non-negative. I should say non-negative. Whenever I say here positive by mistake, it means non-negative. Okay, so we can just pick this n naught, and that will do. That this set is non-empty. And by well ordering principle, it has a least element. Let's call it R. Okay, so this non-empty set has a least element. Call it R. First of all, R belongs to S, so R has to be non-negative. Secondly, R has to be of this form, because S was like that. It was A minus a multiple of B. So that multiple, let me call it Q. So let R be A minus some n b, that n I am calling it Q, or some Q, A minus QB. So to qualify as a remainder, it has to be strictly less than B. Any query? Okay, so we just have to show that R is strictly less than B. Okay, so let's show this. Suppose R were bigger than B. Okay, if possible, let it be bigger than B. Then we'll show a contradiction. Okay, and it's clear that since we are picking it as the least element, so we'll contradict the minimality of R if this, in this situation. Because what we can do, we can subtract B from R, and still we are getting a non-negative integer. Because R is, if R is greater than or equal to B, then R minus B is non-negative. And R minus B, if R is of this form, since R minus B will also be in this form, because R minus B is what? R is A minus QB, then it is minus B. So it's A minus, again some multiple of B. So this R minus B also qualifies to be an element of S, because it is non-negative, because R was bigger than B. And the second qualification is also there, because R minus B is A minus a multiple of B. So R minus B belongs to S. But then that's a problem, because R was the minimum, the least element. And now R minus B is definitely smaller than R, right? Because B is positive. So you are subtracting a positive integer from R. So certainly I'm getting something smaller. Okay, than R. So this contradicts, this contradiction shows that R is less than. So to sum up, to prove division algorithm, we focus on the remainder. We pick it as the least element of a set of non-negative integers, which are yes, A minus A minus. So I suppose you should all be muted. Okay. So I hope you are all muting yourself. Otherwise, it disturbs the class. Okay. So this is the division algorithm. Okay. Okay. And remember, there's a uniqueness part also, because they exist unique integers Q and R. So I just showed the existence first. Okay. This was the existence. This is the existence of quotient and remainder. Now I have to show, because you should know that in mathematics, two questions are important: existence and uniqueness. Okay, just like your MA102 maybe the first order differential equation, there are two important questions: whether it has a solution, and secondly, an initial value problem rather than differential equation. I should say first order initial value problem, that whether the solution exists, and if it exists, whether it is unique. So that's always an important question. So here also we have shown existence by using well ordering principle. Let's see it is whether it's unique, whether it is quotient and remainder unique. So suppose we have two pairs of remainders and quotients. So I'm dividing by B, so I'm getting a remainder strictly less than B, which is non-negative. And suppose I'm also getting a different quotient and a different remainder. Okay, but we'll see that this will force R to be R1, and of course if R is R1, definitely Q has to be Q1. So that's what we're going to show. Okay. I mean, in other words, we'll show that if it's enough to show that R1 cannot be less than R and R cannot be less than R1, because see, this is like if we have two integers, one has to be bigger than the other or they are equal. Okay, one has to be strictly bigger than the other or they are equal. So we'll show that they cannot be, one cannot be strictly bigger than the other. So how do I show? So let's say first, let's rule this out, that R, let R be bigger than R1. Then what do I have? I have R minus R1 is strictly positive, because R is strictly bigger than R1. R is A minus QB and R1 is A minus Q1B. So if I combine it together, I get it as multiple of B with Q1 minus Q. And since this multiple is positive, B is positive, so Q1 should be bigger than Q. Q1 should be bigger than Q. Okay. But that makes R minus R1 is at least 1 times B. So that means R minus R1 is at least B. Okay. See, R minus R1 is positive because of this. And on the other hand, since Q1 minus Q, I mean, it could not be 0. Okay. If it's 0 or if it is negative, there will be a problem because this is B is positive. So this is at least 1. That means R minus R1 is at least B. Okay. But on the other hand, R minus R1 is certainly less than R because R1 is also non-negative. So R minus R1 certainly is strictly less than R, and R is strictly less than B in our choice. So there's a problem that R minus R1 is bigger than equal to B and strictly less than B. So that means B is strictly less than B. Okay, by transitivity, that B is strictly less than B because because this B is dominated by R minus R1, which is strictly dominated by B, which is contradiction. So R1 cannot be bigger than or smaller than R. Similarly, R cannot be smaller than R1. So R has to be R1, and if R is R1, then certainly Q has to be Q1 because B is non-zero. Okay, so that's how we show the uniqueness of quotient and remainder. Okay. Okay, so the next question is, okay, so we are dividing by A was any integer and B was a non-zero positive integer. But let's drop the positivity. Let's say it is any non-zero integer. Can we still get quotient and remainder? Okay, so what we are looking for is A is B times Q plus R, where R is, now I should take R to be less than or equal to mod of B. That's all. Okay, because I want a positive remainder. Okay. So how do I prove this corollary? That if B is positive, then nothing to prove because I mean mod B is B, and this is just what we did before. So let's just see what happens if B is negative. If B is negative, then minus B is positive. So we can perform this operation with minus B. Okay, let's take A and minus B, which is positive. So, sorry. Okay, so let's divide A by minus B. So by division algorithm, for the positive integers, because minus B is positive, A is minus B times Q plus R. What is this R? R should be lying between 0 and minus B. Now, my intention was to divide by B, so I can transfer this minus sign to Q. Okay, so I can transfer this minus sign to Q so that as if I'm dividing A by B, I'm getting minus Q. Let the remainder be same, noting that minus B is the mod B now because B is negative. So this is this. So it's just the direct consequence of existence as well as uniqueness, because this Q and R were unique for minus B, so they'll be unique. Okay. So anyway, so this follows. Okay. Okay, so let's see how we can apply division algorithm to discuss some simple or to how is it useful. Okay. So for example, the square of any integer okay, must not or cannot, okay, must not or cannot leave remainder. Okay, forget must. The square of any integer cannot leave remainder 2 or 3 when divided by 5. Okay, so we can just simply apply division algorithm because any integer n, when I divide by 5, it can be remainder 0, 1, 2, 3 or 4. These are the only choices. So if we square, we'll see that this will give us remainder 0. This will give us remainder 1. This will give us remainder 4. But this will not give us anything new because this will be again remainder like 4, and this one also will give us remainder 1. We can just square and see, because basically it's like when I divide by 5, all this is a multiple of 5 and this is leaving remainder 4 and this is leaving remainder 1. So this way we can clearly use division algorithm to solve some elementary questions. It is just to demonstrate. Okay. Let's do this one using division algorithm. So let's take any integer bigger than 4, and one of n plus 2 or n plus 4 must be composite. That's what we want to show, and using division algorithm. So let's just see what is happening actually. Let's look at the first few triplets. Like if I put n equal to 4, I get 4, 6, 8. If I n equal to 5, I get 5, 7, 9. So it's clear from this tuple particularly that we are getting, I mean, what is the common composite number here? These are both multiples of 3. Okay, because this is multiple of 3 and multiple of 3. So actually we should apply divisibility by 3. Let's see what are the reminders. So clearly, if we divide n by 3, remainders could be 0, 1 or 2. So even in this case, what will be the tuple? What will be the triplet? 3q, 3q plus 2 and 3q plus 4. Or it can be 3q plus 1, 3q plus 3, 3q plus 5. Or 3q plus 2, 3q plus 4, 3q plus 6. So clearly this is like 3 times q plus 2. Okay, so this is a composite number. Okay, and where q is at least 1, because we are starting from n not greater bigger than equal to 4. Okay, and this one also, this 3 times q plus 1. Okay, so this is also composite, and here 3q is composite as long as this is not just 3 itself. So I just have to rule out 3q being equal to 3, but that will be ruled out because my n is bigger than 4, bigger than equal to 4. So certainly this is also a multiple of 3 which is not 3 itself. Okay, so some non-trivial multiple of 3 we find in each of these triplets. That shows that these one of these 3 numbers must be composite. Okay, so as an exercise, you should try that let 2n plus 1 and 3n plus 1 be both squares, and you show that n is divisible by 40. Okay, so if 2n plus 1 and 3n plus 1 are both squares, you should be able to prove using division algorithm that n is divisible by 40. Okay, for example, certainly, I mean, if you put 40, you get like 9 square and 11 square. That's one example. Okay, but yeah, so whenever both are squares, it should be divisible by 40. Okay, so let me see if you have any questions. Do you have any question? You let me know, or I'll move on to the next slides. Okay. Okay, so I hope there is no question. Okay, so let me move on to this notion of divisibility. Okay. Okay, so what do we mean when we say? Let me just open this slide once. Okay, so you are saying, okay, there's a question. Divisibility theorem, what happens if A is negative? Does not matter. What we are dividing does not matter. Suppose I am dividing minus 60 by, say, 9. Okay, so that's not a problem because we can still get a positive remainder. Like minus 60 is 9. Okay, so I mean, it is 9 into minus 7 plus 3, right? So that plus 3 is my remainder. Okay, so minus 60 I'm dividing by 9. So I am getting 9 into minus 7 plus 3. So remainder I can always take it positive. Okay. Any other question? Okay, yeah. Any question you, maybe it's best to put it in the chat box. Okay, so I suppose no question. Okay. Anyway, I would say that put the questions in the chat box. Okay, so divisibility. So when do we say that an integer is divisible by another non-zero integer? Okay, this is all familiar that A should be a multiple of B, I mean with zero remainder basically. That means even in the case of remainder 0. Okay, so remainder 0, we say it is divisible. So we use this symbol that B divides A. Okay, or we can say that B is a factor of A or divisor of A, and A is a multiple of B. Okay, these are all familiar terminology. And of course, we will use this notation. B does not divide A. Okay, but A is not divisible by B. So this is the notation that we are going to use. Okay. So there are certain properties of divisibility that follow quite easily. I mean, some of them are obvious, so we're not going to prove them, but state them, and we'll prove maybe just as a sample 1 or 2. Okay. First thing is that 0 is divisible by any integer, which is non-zero, of course, because when I'm considering divisibility by A, A, B, C, D are integers, but when I'm saying that I'm dividing by A, clearly that means A is non-zero. So 0 is divisible by any non-zero integers, and any integer is divisible by 1, and any integer divides itself, is divisible by itself. These are quite clear. Okay, and if A divides 1, clearly A has to be plus minus 1. Okay, and if A divides B and C divides D, then AC divides BD. Okay, these are some obvious properties. And this transitivity, that A divides B and B divides C, so A divides C. And so you should think of divisibility as if you think of divisibility as a relation, it is reflexive. Like A is related to itself, A divides itself. This transitive, because if A divides B and B divides C, then A divides C. But it is not symmetric, which is required to have divisibility as an equivalence relation. So divisibility is not an equivalence relation because because it is not symmetric. A divides B, but B may not divide A. Okay. In fact, it is what is known as antisymmetric. If we consider natural numbers, what is antisymmetric relation? If A divides B, and if A is related to B and B is related to A, then A has to be equal to B. Okay. So if A divides B and B divides A, this can happen only when A is plus minus B. Okay. So if we stick to only natural numbers, then divisibility is it is not an equivalence relation, it is antisymmetric. Okay, or you can say it's a partial order, because if a relation is reflexive, transitive, and antisymmetric, so it's partial order on natural numbers. Like we can put an order. If something is divisible by something else, we say that okay, there's multiple is bigger than the factor that way. But we may not be able to relate every element. Like 8 and 9, 8 does not divide 8 and 9 does not divide 8. So they will not be comparable. Okay. Okay, so anyway, so yeah, so this is clear. And if A divides B and B is non-zero, then mod A is less than equal to mod B. And this is, although very elementary, but very useful. If A divides B and A divides C, then you take a combination of B and C by multiplying with integers. So this is important. Okay, that if A divides B and C, A divides any integral combination of B and C. Okay, this is like an integral combination. You are familiar with linear combination. You can say it's a linear combination, but with these scalars coming from integers. So this is an important property for us, and this is somewhat obvious, but anyway, let me just prove f and z. Okay, let me just to emphasize how trivial these things are to prove, let's prove f and z. Okay, so let's say A divides B. That means B is AC, where C is non-zero because B is non-zero. Okay, because we said let's say A divides B, and C is non-zero. So what is mod C? Mod C is certainly, okay, so I should have said bigger than equal to 1. Okay, there is a typo here. Because C is non-zero, so that means mod C is at least 1. So it should be in the reverse direction. And then what happens? Mod B, if I take mod here, mod B is mod A mod C, and it is certainly bigger than mod A, because, okay, I should have said equal to, okay, so these are typos. This is not strictly, need not be strictly, it should be bigger than equal to, and this is also bigger than equal to. So these two should be bigger than equal to. Anyway, I'll correct it in my notes when I upload. Okay, I will upload the slides. Okay, so this viewer of these typos. Okay, and secondly, suppose A divides B and A divides C. And let's see what happens to the linear combination. Because what is the meaning of A divides B? B is A times M, and C is A times N. Because of this, C is a multiple of N. So now if I take any Bx plus Cy, clearly what is that? Bx plus Cy is nothing but A times Mx plus A times Ny. So it's a multiple of A. That's all it is saying. Okay, but it is useful. And of course, some of these properties you should always take what will happen rather than just 2 if I take finitely many, or in some cases infinitely many. So certainly there is nothing special about 2. We can extend it to any finite number of multiples of A. In other words, if each BI is a multiple of A, then I can take a combination of all of them, integral linear combination of these BIs, then A will divide all. Okay. So these are some of the properties of divisibility. Okay. Okay, so let's see what is the greatest common divisor, because it's a very important notion. Okay, the greatest common divisor of two integers. Before that, we need to know what is a common divisor. What is a common divisor? So it is, I mean, as the name says, it should be a divisor of both A and B. Okay, so since it is divisor of both, so it's a common divisor. Okay, and this notion can be extended to any set of integers. Even an infinite set we can consider that what is the common divisor. Okay, but anyway, most of the time we'll be applying it to finite set, or in fact 2 elements. Okay, what is the common divisor? Okay, and of course 1 is always a common divisor of any integers. Let's take any 2 integers, then 1 will always be a common divisor. So the set of common divisors of any 2 integers is non-empty, because 1 always belongs there. Okay, okay, so and but yeah, if both are 0, suppose A and B are both 0, then they have infinitely many common divisors, because every natural number will be a divisor of 0, and in this case common divisor. So what do we do when we say greatest common divisor? If we can pick a divisor, common divisor, which is biggest among all, then that will be the greatest common divisor. But we cannot do that if both are 0. So 0 and 0, they do not have any GCD. But if you leave out that trivial case, even if one of them is non-zero, then the other can be 0 also, but their divisors will be finite. The set of common divisors will be a finite set, And in a finite set, we can always pick the maximum element or the greatest element. Okay, and that is called the greatest common divisor, or the GCD. Okay, so if one of them is non-zero, then they will have only finitely many common divisors. So we can pick the largest common divisor, and that's GCD. Okay, so if we give a proper definition, it's like this: let A and B two integers, not both zero. And what is the greatest common divisor? It satisfies these two properties. The D divides A and D divides B. And if C divides A and C divides B, then C should be less than equal to D. Okay. Remember that this is a positive integer. We are saying that greatest common divisor, clearly any negative divisor will have a positive. I mean, if D minus D is a divisor, D is a divisor. Or if D is a divisor, minus D is also a divisor. So positivity we can always impose. Whenever we have some divisor, we can take its absolute value. That will also be a divisor, because that is like changing it by plus minus 1. That is always not a problem, or never a problem. So what is the GCD? It should divide both, and if anything else divides both, then it should be less than D. Okay, and we write like this, that D is the GCD of AB, and sometimes we drop even the word GCD. It's clear that sometimes D is AB. Okay. Okay, so now let's see that GCD is actually a linear combination of the integers that we are considering. Okay, let me first give an example. Okay, and by the way, all this might be too familiar with you, but anyway, we have to do it this way. And secondly, these things are generalized to rings later on. Okay, because in rings also we can have this notion of divisibility. Okay, and we can talk about GCD and LCM in arbitrary rings also. I mean, not, I mean, in more general rings. Okay, and then this question is important, whether the GCD is a linear combination or not. But for integers, it is a very classical question, and yeah, it is a linear combination. So let's look at 24 and minus 60. Clearly, what are the common divisors? We can easily list them. Okay, and we see that 12 is the GCD. Okay, and we observe that this GCD can be written as a linear multiple of 24 and minus 60, because I can multiply minus 60 by minus 1 and 24 by minus 2. I get 60 minus 48, which is 12. Okay, so I'm getting the GCD of A and B as an integral multiple of A plus an integral multiple of B. Or in other words, the GCD of A and B is appearing as an integral linear combination of A and B. Okay, and so we want to insist that this is not a coincidence for just 24 and minus 60. It will always happen. Okay, so this is not a coincidence. So the theorem is, let A and B any two integers, not both zero. Then there exist integers m and n such that GCD is an integral combination of A and B, where these integers, these are integers. Okay, and they can be negative, of course. We're not saying natural numbers, because if we just say natural numbers, it will certainly need not be true. Okay, I mean, clear, because GCD should be smaller than, say, let's say I'm taking two positive integers. So GCD should be smaller than them. But if we are only taking natural numbers, certainly this number will be bigger than A or B. Okay, so certainly trivially also it can be ruled out. But yeah, it's true for integers. So let's see how this is true. So what we have to do is again apply well ordering principle to a suitable set. Okay, so what will be the suitable set in this case? It will be the set S consisting of all positive linear combinations of A and B. In other words, what is my set as? Is ax plus by, where it is x plus by should be positive, okay, and xy, as xy runs over integers. And first I have to ensure that this set is non-empty. So I have to produce some suitable x and suitable y such that a times x plus b times y is positive. And it is not hard because I can just choose x to be a and y to be b. Then I'll get a square plus b square. And a square plus b square will be positive because not both a and b are 0. Because when we are trying to find GCD, we have already ruled out both being 0. So at least in a square plus b square, at least one is non-zero. So a square plus b square will be positive. Okay. So, okay, so yeah, so this should not have been a capital Y. But anyway. Okay, let me see if it is a comment or is it something else. Okay, not a comment. Yeah. Okay, so this is a non-empty set of positive integers. So it will have a least element. Okay, and we'll claim that that is the GCD. Okay, we claim that this has a least element D, which is the GCD. Okay, how do we do that? We have to show that D divides A and D divides B. So in other words, first of all, to qualify as a GCD, it has to be a common divisor. And it will be enough to show D divides A because similar argument can be applied to B also. That will show that D divides A and D divides B. Once we have that, the other part is clear. That if C divides A and C divides B, okay, C should be less than D. Okay, so let's see anyway. Okay, so by division algorithm, how do I show that D divides A? I just have to show that when we divide D by A, the remainder should be 0. Okay, so apply a division algorithm. There will be integers Q and R such that A is DQ plus R. What is R? It should lie between 0 and strictly less than D. Okay, this is my intention is to show that R has to be 0. Okay, so what is R? R is A minus DQ. Okay, and what is D? Since D is a member of S, it is the least element of this set. So D is AM plus BN for some Mn n belonging to Z. So, okay, there is a typo here, it should be Q. Anyway, I'll correct this. So remember that I'm substituting not Q, but I'm substituting D. So it should have been A minus D, I'm replacing by this, and this is actually Q. Okay, this should be Q. So it is A minus MQ actually. This is MQ. Okay, and this should be NQ. Okay, but whatever it is an integral combination of A and B because this is an integer and this is an integer. Which these are not D's but these are Q's. But what we want to emphasize it is A times some X plus B times some Y. So this R also qualifies to be an element of S if it were positive. So only thing that stops R from being a member of S is its positivity. Okay, so maybe it is not positive. Okay, but if it is positive, then I will be in trouble because I picked the least element. Now I am finding another element which is in S. Okay, so it will contradict the minimality of D in S. Okay, so that shows that this remainder is 0 and D divides A. Similarly, D divides B. Okay, so okay, so let me. So it is just the well ordering principle. You can see how useful it is. You just have to pick your choose your set carefully. And in this case, we chose it to be, since we were interested in showing the GCD as an integral combination. So we took the set of integral combinations as the set S, insisting that it is the positive combinations I am taking. Okay, and since it is non-empty, it had the least element D. And we have to show that first of all that D divides, it's a common divisor. So So we just gave the argument for D dividing A, because if we have a remainder, then if it will be also a combination of integral combination of A and B, and hence it cannot be positive, because if it is positive, then it will contradict the minimality of D. So, and the second property, what is the second property for GCD? That if C divides A and C divides B, C should be less than D. Okay. So how do I do that? But it is clear now, because suppose C divides A and C divides B, then certainly C divides AM plus BN. That is one of the divisibility property, that if C divides A and C divides B, then certainly C divides D. Now if C divides D, certainly mod C is less than equal to mod D. Okay. But mod D is D, so that means C is less than D. Okay. Anyway, so that part I'll show you as a part of my lecture notes rather than the slides. Okay. So let me just show you. Okay, not this, not this. Lecture 3. Okay, so this is the one. Okay, so now let me just share this. So what we have, I am yet to convert it to slides. Okay, but doesn't matter. So far we have showed. So I'll increase the font now. Okay, so we are here. Okay, so that we have shown that the common divisor, it's a common divisor. Now let's say C divides A and C divides B. Now what we need to show that C is less than equal to D, but C divides AM plus BN and D is AM plus BN. Okay, so this is what concludes the proof. Okay, so now that's a very important notion of being relatively prime. So what is relatively prime? So if the GCD is 1, we say it's relatively prime. Again, these are all notions that you are familiar with from your school days. Just that we are basically proving some of these which statements which are intuitively true, which seem intuitively true, but we are just proving them starting with well-ordered principle. So two integers, anyway, we do not consider a case when both are 0. They are said to be relatively prime if GCD is 1. Okay. And then what does this corollary say? Okay, I cannot increase in this. That if A and B are integers, not both 0, then A and B are relatively prime if and only if there exist integers M and N such that AM plus BN equal to 1. Okay, remember the theorem already, the previous theorem already proves one part, that if 1 is the GCD, there will be integers M and N such that AM plus BN equal to 1. So that part is already there. So that is the implication, I mean the forward implication. So let's go to the backward implication. So let's say let AM plus BN be 1, and I want to say that GCD of A and B is 1. How do I do that? Take any common divisor C of A and B, and C divides A and C divides B implies C divides AM plus BN. That means C divides 1. Okay, so that means C is less than equal to 1. So any divisor, common divisor of A and B is less than equal to 1. That makes GCD 1. Okay, so it's quite trivial, though useful, but it is actually a trivial proof, but it is useful. Okay, and this notion in general also in other rings we will see later. Okay, that when they are co-prime, is it like you can find a combination with ring elements like this. So this is okay. This is what we do. Another thing which is also obvious is if D is the GCD of two integers A and B, and GCD of A by D and B by D is 1. Okay, you factor out the GCD, then you get co-prime integers, which is quite obvious. But let's prove it using the theory that we have built up. Okay. So if D is the GCD of A and B, so I can write D as a combination of A and B with some integers M and N. And I just divide by D both sides. I divide this by D. So I get 1. And since A is divisible by D, I can say that it is A by D times M plus B by D by N. Remember that these are integers. These are not fractions. Because D is a common divisor of A and B. GCD. So that means I am getting 1 as an integral combination of M and N. And that makes, integral combination of A by D and B by D. So that means A by D and B by D, they are co-prime. In fact, these M and N are also co-prime. You look at the other way. But we are not interested in M and N. Okay. But if we are getting this combination, this with this will be co-prime, this will be co-prime, or this with that will be co-prime, and because otherwise any common factor of this and this will divide 1. Okay. So, but anyway, we are interested in pairing A by D with B by D. They have to be co-prime. They will be relatively prime. Okay, relatively prime and co-prime, of course, they are the same thing. And if A divides C and B divides C, where GCD of AB is 1, then AB also divides C. Remember, this is important. Otherwise, what will happen? Like 4 divides. Okay, so you can easily find the contradiction, right? If they are not co-prime. Okay. Because like 4 divides 8 and 4 divides 8, let's take that. Then I cannot say 16 divides 8. Okay, certainly I need this to be co-prime. Okay. And when they're co-prime, it is easy again. So what do we do? Since C is a multiple of A, so C is AR. And C is a multiple of B, so C is BS. Okay. When GCD is 1, then I can write 1 as a combination of A and B, because this is GCD is 1. So if I combine all that, and I want to look at divisibility of C, so clearly the thing to be done is you multiply this by C. You multiply both sides by C. So you get C is ACM plus BCM, you just multiply. But C you replace by BS first and then AR here. Why? Because already A is there. So I now want to see C as a multiple of B I use here. And C, since B is already a factor here, I want C as a multiple of A. So then I can see this. Okay, that C is a multiple of AB. Okay. And this is a very important property. It is very useful, although it's very simple, but it is most useful. Okay. This will be clear when we define prime and irreducible, what we say. Because although it's a bit ahead, so what is a prime number? There are 2 ways to view it. One is you cannot factorize it further in a non-trivial way. So what are prime numbers? They cannot be factorized. Written as a product of AB. If you write them as a product of AB, then A has to be plus minus 1 or B has to be plus minus 1. Those are prime numbers. On the other hand, you can see define prime number also as if P divides AB, then P divides A or P divides B. And later on, for integers, we'll see that these are same properties. But in general rings, that divisibility property is much stronger and often is stronger. And that factorization property is actually weaker. Okay, but for us, just I said before is just to emphasize that this is something important for us. Okay, so Euclid's lemma, what does it say? That if A divides BC and A and B are co-prime, then A is to divide C. And why is that? Let's